In our previous lessons, we have learned the concept of dynamic memory allocation. We have understood what is stack and what is heap in applications memory. Now in this lesson we are going to talk about one situation which is caused by improper use of dynamic memory or the memory on the heap, and this situation is memory leak. A quick recap of some of the concepts that we have discussed in our previous lessons. The memory that is allocated for the execution of a program, or what we can also call applications memory, is typically divided into these four segments or these four sections. One section stores the instructions in the program that need to be executed. This section is called the code segment or the text segment. Another section is used to store the global variables, the variables that are not declared inside functions and have lifetime of the whole application. Another section of the memory is used to execute the function calls and store all the local variables. This section is called stack. The size of these three segments, the code segment, the global variable segment, and the stack segment, are fixed and decided when the program is compiling, that is at the compile time. And the fourth section, which is called heap or dynamic memory, does not have a fixed size. Heap can grow as per our need. As we know, we get memory from the heap by making a call to malloc function in C, and when we are done using that memory on the heap, we make a call to the free function to deallocate or free that particular memory. In C++, apart from malloc and free, we can also use the operator new to get some memory and the operator delete to free that memory. Memory leak is a situation when we get some memory on the heap and do not free it when we are done using it. So our application is actually holding on to some unused memory on the heap. But why do we call this situation memory leak, and why does it happen due to improper use of dynamic memory only, due to improper use of heap only, and not some other sections of applications memory? We will try to understand this through one simple program. So what I'll do is I'll write one simple program and show the simulation of its execution in the memory to explain these concepts. In my C program here, I'm going to write a very simple betting game, and the game is that we have three positions and three cards: Jack, Queen, and King. Initially Jack is at the first position, Queen is at the second position, and King is at the third position. And then computer shuffles these cards so that the positions of these cards is changed, is randomized, and now the player has to guess the position of the Queen. He has to bet some amount of money, let's say it's virtual cash, and if he wins, if he predicts the position, if he guesses the position of Queen correctly, he takes away 3 times the amount that he had bet, and if he loses, he simply loses the bet amount. Let's say the player initially has $100 of virtual cash, and he can play as many times as he wants until he runs out of cash. So let us now implement this game. The first thing that I want to do is I want to declare a global variable named cash that at any point will store the virtual cash available with the player. Initially he has $100 of virtual cash, and then in the main method I will declare a variable named bet, and I will write code something like this. While cash is greater than 0, while player still has some cash, we will ask him to bet something, and we will take this input in this variable bet using scanf. For negative scenarios like bet equals 0 or bet being greater than the cash available, let's say we will break out of this loop, we will end our game. For all other conditions, let's say we will make a call to play function, and of course now we will have to write the play function. We will be passing bet to the play function, so bet will be an argument. And now in the play function I will declare a character array of size 3, and initially we will have the character J at the first position to say that there is a Jack at the first position. J is for Jack, and similarly Q is for Queen and K is for King. And now the computer must perform a randomized shuffling So we will write a print statement like this. Now we need to find a logic to make a random shuffle of cards. One such logic is that we can make a call to random number generator function in C to use the random number generator. First we will make a call to srand function and pass it an argument something like this. I'll come back to what I'm doing here in srand by making a call to srand. Now let's say we run a loop 5 times and we will choose any two random positions among 0, 1 and 2 and swap the letters at these positions in the array. Let's say these positions are x and y. Now when we make a call to rand function, we will get a random number, but we want a number between 0 and 2 included. So we will take a modulo by 3 so that we either get 0 or 1 or 2. So we will take two such random positions with statements like this. And now what we can do is we can swap the characters at these positions. So we will use a temporary variable. First we will store the character at position x in temp, and then we will do something like this. I'm short of space here, so I'm writing 3 statements in the same line. Okay, so now the swapping is done. So we are swapping or shuffling characters at 2 positions 5 times. Each time we are picking up 2 positions x and y randomly by making call to rand function and taking a modulo by 3. So this will guarantee us that x and y is between 0 and 2. That will be valid positions. By making a call to rand function, we will get the random numbers, but we also use this srand once and pass this time null, the return of time function. In random number generation, there is one concept of seeding the random number generator. So we are passing seed to random number generator. We will not go into the details of random number generation now. Now what I'll do in the play function is I'll have a variable named player's guess, and I'll ask the player to guess the position of queen, and then I will use scanf to take the input. Now if the player is correct, then the character at that particular position in the character array C, and the position will be 1 minus what the player inputs. Because the player is inputting 1, 2 or 3, that will map to 0, 1 and 2 in the array. So if the character is queen, he has 1, so his overall cash will be incremented by 3 times the bet amount. Else he has lost and his cash will be decremented by the bet amount. So in the case of win, we will write a print statement like this. We will say that you have won and the result is this, and your total cash right now is this. Remember, cash is a global variable, and we will print something similar if the player loses. Finally, our play function is looking something like this, and we have also moved this variable cash at the top. In the main method, I've added 2 more print statements initially. Let's now play this game and see what happens. What I have done is I have compiled this code and created an executable named game.exe, and now I'm going to run that executable. So this is asking what's your bet. Let's say we want to bet $5 on position 1, and I lose. My balance now is $95. Let's bet again. This time again I lose, and I can go on playing. So I'm losing again and again. Finally a win after a long time. I can go on playing this game, but I want to show you something else. I have opened the task manager of Windows, and here as you can see this highlighted row is for game.exe. The third column here is the memory consumed by this executable game.exe. You will have to see this in full screen. Now as I go on playing, the memory consumption here, the memory that's showing here, is not increasing. It's always 348K. Now I'll go ahead and make some changes in my code. What I'll do here is this particular character array that I'm creating as a local variable in the play function. Right now it's created as a local variable, so it will go on the stack. Now I want to create a character array on the heap. So what I'll do is I'll write statement like this. I'll declare a character pointer named C, and then I'll use malloc to fetch memory to store 3 character variables. In C++ we could have said something like this. We could have used the new operator. And now I'll set value at 0th index as j, 1th index as q, and 2th index as k. So we have created an array on the heap, and C is a pointer to the base address of that array. C is still a local variable, but now it is a pointer to character, and we can still use it like array. The rest of the code will just work fine. Let us run this code and see what happens. I have opened the task manager and I'm running the executable. Watch for the memory consumption of game.exe. I will make some bets. As you can see right now, the memory consumption is 348K. I just kept on playing, and after some time the memory consumption is 488K. It has shot up, and if you will keep playing this game further, after some time it will shoot up again. Maybe after some time, but it will shoot up for sure. So why is it happening? Why was it not shooting up when C, the character array, was not on the stack, not on the heap, and it was on the stack? Let's try to understand. I have drawn sections of applications memory here, and let us now see what really happens in the memory when we are playing our game. As we know from our previous lessons, all the information about function call execution goes into the stack section of the memory. Anytime a function is called, some amount of memory from the stack is allocated for its execution. When the program starts executing, first the main method is invoked or called. So let's say some amount of memory is allocated for the execution of main. This is what we call the stack frame of a function. So this is stack frame of main, and all the local variables of main will sit inside this stack frame. In our code we had a local variable named bet, so it will go here, and we had a global variable named cache. So initially, let's say main function is executing. When we play our game, main function makes multiple calls to play function. What really happens when a function makes call to another function is that that particular function is paused and memory is allocated for the execution of the called function. So main will pause and play will start executing, and play will go on top of main in the stack. We had a couple of local variables in play. All will go in this stack frame: I, X, Y, player's guess. And for the case 1, when we had the character array C on the stack itself, so it was not created using a call to malloc, the character array C will also sit in this stack frame. Now when the execution of play function will finish, control will return back to main, and the memory that was allocated for the execution of play function will be reclaimed. Anytime a function call finishes, the memory that it is allocated on the stack is reclaimed. So there is one stack frame corresponding to each call, and as soon as that call finishes, that memory is claimed back. Now main will make another call to play, because we will play multiple rounds, so play will again come into the stack, and it will be cleared again when play finishes. As you can see, all the local variables get cleared each time the function call finishes. For anything on the stack, we do not have to worry about its deallocation. It happens automatically when the function call finishes. Now let's talk about the second case, when character array is created on the heap using a call to malloc function. Once again, we will make multiple calls to play function. Now what will happen this time is that we will not create the array on the stack. We will still have a variable named C, a local variable named C, but this variable will not be of type character array of size 3. This variable will be of type pointer to character, and we will make a call to malloc function to create the array on the heap. And this local variable, which is a pointer to character, will only point to this particular memory block. Anything that is on the heap has to be accessed through a pointer variable. So here we have created the array on the heap, and we have kept only a pointer variable on the stack. Now when the call to play function will finish, the memory allocated for the execution of call to play function will be reclaimed, so all the local variables will go away, but this memory on the heap will lie unused and unreferenced, and it will not get deallocated. Anything on the heap has to be explicitly deallocated by making a call to free function or by using delete operator. And think about it, we will make multiple calls to play function as we play multiple rounds of our game, and each time in each call to play we will create one such memory block on the heap that will lie unreferenced and unused when call to play function will finish. if we will play our game 100 rounds, then we will have 100 such unreferenced and unused memory blocks of 3 characters in the heap. Heap is not fixed in size, and our application can get more memory in the heap section as long as our system itself is not running out of memory. And if we are not deallocating this unused memory on the heap, we are depleting and wasting memory, which is an important resource. Our application's memory consumption will only keep on growing with time. Memory leaks are really nasty bugs to have in your program. Anything unused and unreferenced on the heap is garbage. In C or C++, we have to make sure as programmers that garbage is not created on the heap. Memory leak is nothing but growth of garbage in the heap. In languages like Java and C#, garbage is automatically cleared from the heap. So programmer does not have to worry about freeing or deallocating the memory on heap, which is a cool feature to have. It avoids memory leak. In this example, we were creating an array of 3 characters on the heap. What if we were creating an array of 10,000 characters and not freeing the memory after we were done using it at the end of the function? The memory consumption would have shot up like anything. Coming back to my code here, what I have done is I have created a character array of size 10,000 of 10,000 characters here. My logic would not change. I'll just use first 3 positions in the array. I'm just trying to show you something, and at the end of this particular function, when we are done using this array on the heap, we are making a call to the free function, passing it the address of this memory block, this array C. Our program will just work like before, but let's run this and monitor the memory consumption once again. I'm showing you the task manager and I'm playing the game. Let's make some bets. Now watch out the memory consumption of game.exe. For howsoever long you will play the game, the memory consumption won't shoot up. As you can see, it's 356K and it's not shooting up for me even after playing for a long time. And it is not shooting up because we had used free to deallocate the memory when we were done using it at the end of the function. Remember, we had created an array of size 10,000, and if we were not using free, then the memory would have shot up like anything. The memory consumption would have shot up like anything, but because we are freeing at the end of the function, it's not going up. There is no memory leak. So finally, to summarize it, memory leak is improper use of dynamic memory or the heap section of memory that causes the memory consumption of our program to increase over a period of time. Remember, memory leak always happens because of unused and unreferenced memory blocks in the heap. Anything on the stack is deallocated automatically, and stack is always fixed in size. At the most, we can have an overflow in stack. So this was memory leak in C++. Thanks for watching.